Yeah, that'll be cool. I hacked up a little EPC a long time ago, and think I was putting a GPS inside or a USB drive or something, and it started getting really hot. And it turned out when I had put something in and I closed the keyboard down, I was squashing the fan, and the fan wasn't spinning. And I did a temperature check, and it was up to something ridiculous, like I think it was like 170 Fahrenheit. It was insane. And it didn't fail, but it was getting like really uncomfortable to touch. So yeah, they're pretty durable.
Well, I opened up my computer and found there are like 3 fans that should be running that aren't running.
Oh really?
So I don't know what's going on there. Because I've had problems with my rear fan before. The specific model of computer I have, it had a problem where the fan would like move back and start hitting the back of the computer. My new fan that is in there now doesn't do that. It's just deciding not to spin.
Some of that software control, most of that software controllable too.
Yeah.
So it could actually be a setting. Or you can just cut the wires and put a switch on.
Well, sometimes I'm able to like spin it manually, like a little bit.
Yeah.
It'll start spinning a little bit.
Oh really? Okay.
So it starts going on its own if you.
So
give
maybe
a
it just
little
needs some cleaning.
Yeah,
or replacement.
Well, that is something that I tried. Is I did the air.
Yeah.
Brush basically, and that worked a little bit.
Mm-hmm.
And next time I tried it, didn't work at all.
Yeah,
so
it could be gummed up inside.
possibly.
They're usually pretty easy to swap out.
I mean, I've only had it for a few months,
Yeah.
so that's why it's a little concerning.
Yeah. All right, so let's talk about Lab 4 really briefly. Lab 4, you're playing with the input side of working with the Pi. So you've done some LED flashing, those are outputs. Now you want to do some reading of input. And we're going to read a switch. Okay, so our switches, there's a switch in your parts box. There should be, it's a little 4-legged thing with a black circle on top that you can press. It's spring loaded, so it looks different from the regular 250, 270 switches. But electrically, it still looks like this, right? Basically, it's an open circuit, and when you press the button down, it makes contact between 2 points. There's 4 legs. Get a multimeter, measure the resistance between the legs, figure out which ones are connected and disconnected when you push or release, okay? That's not in the lab report, but that's how you figure out what a switch does. And then you want to hook it up to your Pi, and we're using the same pins we used for the LED, pins 14 and 16. 14 is ground, 16 is GPIO number 4. Okay, so same connection as before, but you're going to read from this switch instead of writing. And your basic goal is to basically detect when the button is pressed. And you're going to do this by polling. We're not doing interrupts here, we're just polling. So here's a flow chart. So we do some initialization. And then check to see if the button's pressed. And do something accordingly. And that's the life of your Pi. So it's just a loop. Okay. Check the button, do something, check the button, do something. So what do? We want to count how many times the button's been pressed. So you need a counter. Initialize it to 0. Every time you detect the button has been pressed, add 1 to the counter and print it out. Okay, so you press the button and you see a 1, you press the button again, you see a 2. Pretty basic behavior. How do you know when the button has been pressed? Because all we have is make contact, break contact. So you have to do something like what you've done in 270. You have to look at the button initially and say, is it open or closed? Am I seeing a 1 or a 0? Okay. If you're seeing a 0, which is what you'll see when the button's not pressed, make a note of that, set a flag somewhere, go back, check again. Am I seeing a 0? The first time that you see a 1, you know the button just got pressed. And at that point, add 1 to your counter and make a note that the button is currently pressed. The next time you check the button, you see a 1, but you also know that your button was a 1 the previous time. That's not a new button press. It just means the button is being held down. Does that make sense? Okay, so this is stateful again. You've got two states. Button has been pressed, button is released. If the button's released and you see a 1, that's a button press. If the button is pressed and you see a 1, that's nothing. The button's being held. If you see a 0 and the button was pressed, that's a release and you still don't have to do anything. And if you see a 0 and the button is released, it's still not being pressed. You don't have to do anything. So the only time you really care is when the last time through you saw a 0, but now you're seeing a 1. And then you say, aha, the button's been pressed. Let's go ahead and add a 1 to our counter and print it out. All right, and there's a bonus opportunity here, which is these switches are mechanical. They're imperfect. So an ideal switch, when you're not pressing the button, there's no connection between these 2 points. When you press it, it makes contact. And we're basically counting how many times we change from no contact to contact. And ideally, that would be once per press, but in practice, it's not. There's bounce in these switches. So when this piece of metal comes down, it's fighting a spring and it makes contact with another piece of metal. That second piece of metal may deform a little bit. There may be some pushback from this, and it's going to actually make and break contact multiple times. So what you'll see when you code this up is probably each time you push the button, instead of just adding 1 to your counter, it's going to add 1, print it out, add 1, print it out, and it's going to do that multiple times. And so it may look like each button press gives you 3 or 4 presses. Okay, that's called switch bounce. There's different ways to get rid of switch bounce. One way is through software. So your bonus points come by doing some software-based debouncing. So you can use system.currentTime_millis to find the current time on your Pi in milliseconds. And the idea is the first time that you detect the button is pressed, make a note of what the current time is. The next time you see the button being pressed, compare that to the previous time. If it's only been 5 milliseconds since the last button press, it's probably a phantom bounce. Unless this person's really hitting this button 200 times a second, right? Which they're probably not. So you're going to have to play with it. You're going to have to figure out what's a reasonable amount of time to wait. If you waited 2,000 milliseconds, right, it's only going to take button presses every 2 seconds. And if you try to hit your button faster, it's not going to notice. That's not good. But if you make the interval too short and you've got just the right touch, you press the button once, it might think you pressed twice or 3 times. So you got to play around with what that interval is, right? Make it a variable, do some experimenting. This is all stuff you talk about in the lab report. And when you get that nailed down in a good spot, right, you can come in and at a reasonable speed, you can hit the button 10 times and it'll count 10 clicks. All right, so that's your bonus part. So your sign-off sheet, when you demo this, make sure you demo this and get a sign-off sheet and put this in your lab report, okay? So one experiment, you want to make sure each time you press the button, you get at least 1 message. And that message shows the number of counts, and the counts increases at each button press. And it's okay if it increases by more than 1. For the bonus, it should increase by exactly 1. And you should be able to press it 10 times at a reasonable speed and have it count exactly 10 clicks. Okay, demonstrate those and get a witness signature, and you got your bonus points. Does that make sense? All right, possibly helpful code fragments. So this import was missing from the version on Canvas, but I posted an announcement with it. I don't think I reposted this, but make sure you import pi4j.wiringpi. That gets you some of the classes you need. So the Gpio Factory is exactly the same. Okay, you get an instance of the factory that gives you a controller. But here, we construct a GPIO pin digital input instead of output. And when we use provision digital input, we give it the GPIO number, which is GPIO 4. That's pin 16 on the side of the Pi. And here we've got a great little goodie, GPIO pull-up down control for comma GPIO dot pull up down underscore up. So what's going on there? Well, every time that we talk about switches in 250, 270, if you've ever had those courses with me, I tell you this is the only way to wire a switch. Right, this goes to your circuit. You got to pull it up through a 1K resistor to VCC and then use the switch to optionally ground it out. And we're not doing this. Right? I didn't mention that you had to use a resistor, and I don't think there's a resistor in your parts box, and there's no VCC. We don't need to do this because the Raspberry Pi, like most devices, will let you specify, I want an internal pull-up resistor. And this line right here where you say pull-up down control and you set it to pull-up down underscore up, that will electrically wire in a 1K pull-up resistor tied to VCC on that input line. So with that enabled, all we have to do is either leave it open or connect it to ground. And if we leave it open, it's not actually floating, it's being pulled up internally to a logic 1. If we connect it to ground, then it's being pulled down to a logic 0. So wiring these things really, really easy. Okay, it's just a single open-close switch. But you gotta have that magic line, otherwise it floats when it's disconnected. So that's your pull-up. And then here's just a sample loop. So pin.getState will return basically a 1 or a 0. But you can compare it to pinState.high. If it matches that, then it's seeing a 1, otherwise it's seeing a logic 0. So we're just interrogating here to turn that into an integer, and then you can do whatever you want with that. So that's your setup, right? Set up the digital input pin, set up the pull up down, and then to read the state, you basically just use pin.getState. And then the rest is just plain old Java code. Good to go. All right, so have fun with that. That gets you the input side, and then in lab 5, we put them both together and we do input and output, and we build a small network. So we'll keep adding to this. All right, so PA3 questions. We didn't get time to talk about it yesterday, but graded it and put back comments. So a lot of people were completely successful in getting a tic-tac-toe game, which is great. A number of people were not able to get it completely working, but the GUI part of it, the Java part of it, the swing part of it, I don't think was the real issue, right? It was more this idea of sort of maintaining a notion of state and modifying that notion. And that's an easier problem to rectify in some sense, right? So the Java part, dealing with the objects, things like that, felt like most people were on top of that. The troubles that people seem to be having were things along the lines of how do I make the computer make a move after the user clicks, right? So you move the mouse, you click, you get a mouse event, you decode the coordinates, you figure out row and column, you update your array, you call repaint, and your paint method paints an X where the user goes, okay? That's like 80% of the challenge right there. And most people got, some version of that working. If you want the computer to move at that point, before you exit, right, if you exit at that point, then you've painted an X where the user clicked, and now nothing is going to happen until the user clicks again. Okay? If you want the computer to make a move at that point, it's really just a matter of calling some code which decides where the computer wants to go, and then does exactly what you just did for the user's move. Update your data structure, your array, right, to say, okay, this is where the computer's mark is. Call repaint, and exit. So every time you click, you do a set of things. You basically do those twice. You do it once for the user based on where they clicked, and then you do it again for the computer based on where the computer wants to go, which can be a random open square, or it can be the next open square, or it can be something more clever. And then the other details are things like not being able to finish the game, right? The game, three marks end up in a row, and you draw the winning line, but then nothing else happens after that. It gets frozen. In some cases, it totally hung. I couldn't even kill it by Xing it out. I had to like forcibly kill the process. So that's, again, a matter of sort of thinking through what the overall state transitions are in your game. Right? You have maybe your initial state when you're waiting for the user to make selections and hit the start button. And you leave that state when the start button's pressed, and you go into a state where you're waiting for mouse clicks, indicating moves. And you stay in that state until either there's no squares left or somebody wins. And then you go into a new state where you're basically waiting for the person to say, start the game. So in some cases, it's a matter of having this final state where the game's over, and now every time that you get a mouse click, you don't do anything, right? You're basically just waiting until the start button gets pressed. And when the start button is pressed, you have to check to see, am I in the very beginning state? Am I at the state where I just finished a game? And treat those things basically equally. So if you didn't get all the way through to the end with PA3, definitely come by and let's go through your code. Okay, because like I say, in most cases, I think it's really close. And it's worth, I think, spending the energy while it's fresh in your minds to figure out what the last details were. Okay, so definitely catch me in office or ask me questions somewhere, and we can get PA3 working completely. Yeah.
I know one thing that happened in my set of code. This might have something to do with just how it's possible that the way I had it set up, since it's in front of me, I can't see it, but I might have initialized like the player's icon right at the beginning and never revisited it.
Okay.
But whenever I would reset the game, like it wouldn't let me switch what my icon was. It would keep me at the old icon.
Interesting.
And the other thing about that is like, this probably has something to do with repaint, but after I would reset the board, nothing would change until I clicked in there again.
Yes, right, I remember that.
So is that just repaint?
I think it was your code I actually dug into, and I didn't see it initially, right? The first thing you would think is that you're not calling repaint, but you were, right? And you seem to be calling it after you've done all these things.
Yeah, that was why it was confusing, because I thought when I first thought of it, it's like, oh, I must have put it before that, so it wouldn't read it after all the arrays were updated, but it definitely
yeah. So we got to go through there and figure out where you actually clear the board out, right? Clear your data structure for the board, and make sure that repaint's getting called after that. Right. Because I think you called repaint like 15 times throughout different things you were doing, and it looked like every time that something changed state, you were calling it. So I couldn't find that one, but we can look at it.
Well, that would be under like the reset method, because I had a separate.
I didn't look in there
for that. So.
Okay, yeah, come by. We'll dig into it. What was the first thing you said?
About switching icons.
Switching icons, yeah.
That screams to me, now that I'm thinking about it more, an initialization issue where it doesn't ever revisit that thing. So that's probably just a state issue.
Yeah, and maybe you're looking at the wrong event handler. When they switch it, it's not triggering the code you think it is. Yeah. So yeah, we can nail those down pretty quickly, I think. All right, so let's talk a little about PA4. And PA4 is, in some ways, a very simple algorithm from a top level point of view. basically read your decision tree from a file, okay, which is specified in a string called database, hopefully. So you ingest this tree from a file, and then play the game. So start at the root, print out questions, get answers, keep going until you get to a leaf node. If your answer is correct, then you just go back and play the game again. You can be polite, put something like, would you like to play again, and have them say yes, no, or something like that. Or you can just force them to play for the rest of eternity, whatever. So if the answer is correct, just go back and play the game again. If the answer is incorrect, adjust the tree in memory. So ask them for what the correct answer was, ask them for a question that discriminates the correct answer from the answer you came up with. Modify that point in your tree in memory, okay? And then write your tree to the file. And then go back and play the game again. And that's really kind of the top level view of the whole assignment.
You said this was 20 questions?
Yeah.
Okay.
Yeah. You're not limited to 20.
Okay.
So one thing to note here is you only read from the file once, which is in the very beginning. Okay, and we talked about this recursive, I think I used the name ingest for the routine. And if you write it recursively, it's a few lines of code. You write to the file from your memory tree. That's just a pre-order traversal where you write out. So we read from the file once, and then we just keep dumping our tree into the file every time the tree gets changed. Okay? There's no sort of back and forth in the file itself. Right? You don't want to find yourself writing code where you read the file and you analyze it and do some things and write it back again and again and again. The only time you should be reading the file is in the very beginning. Okay? Everything else is just your tree in memory, and when you modify it, write it out to your file before you play the game again. So all your hard work is being done on your data structure in memory. Okay, and all of your playing of the game comes from reading that structure that's in memory. Is that clear? So we know how to read from a file. You know how to read from standard in, right? You just open the scanner on system.in. Well, sc.has next line, you use sc.next line. Because our decision tree in memory is organized one line, one piece of information per line, right? So you can use next line and has next line. So if you want to read from a file instead of system in, you can do something like this. So new scanner, but when you construct your scanner, use a file constructed from whatever the path name is for your file. So if it's a string called database, you could just do something like this. So this creates a file object constructed for whatever the name of your file is. And that will always succeed. That doesn't throw an exception even if the file doesn't exist. But this will try to construct a scanner to ingest from this file, and if the file doesn't exist or isn't readable, this will throw an exception. So Eclipse will force you to throw this whole thing inside a try-catch block. And go ahead and do that. And then you just use the scanner object input in this case the same way you used scanners throughout everything we've done so far. So that's how we read, but we haven't talked about how to write. So probably the easiest way to do output to a file is to use something called a Printwriter. So we construct it. And we can give the constructor an argument which is a file. So we can say new file, database. Let me get this up before I switch back. So construct a Printwriter with a new file, and this can throw an exception too, so you have to put it in a try catch. And then when you want to do output, you can just say pw.println and put any string in there you want. And it works like system.out.println. So questions about Printwriter? All right, open it up, right, and be kind, go ahead and close it when you're done. If you don't close it, it will get closed when your program exits, but if your program doesn't exit, then it may not get written. And if you Control-C your program to exit immediately, it may not get written. So you definitely want to close it after you're done writing into it. So you should always be writing sample code, right? Anytime we encounter something like this, try it out. So here's some sample Printwriter code. So you have to import it, but as usual, Eclipse will pick up the imports for you. So I'm declaring my Printwriter outside of my try block. If I declare it right down here, if I say Printwriter PW at this point, I don't have access to PW outside of the try block. Right? It's local to that. And unless I put all my code in the try block, I'm going to get syntax errors. And you don't usually want to overload your try blocks. You want them to do the piece that might fail, right? So I declare my Printwriter up here. I give it a null value just so the compiler doesn't warn me that it might not have a value. And then here I'm just making a file in my home directory called haha. Creating a new Printwriter for that, calling it PW, and then I can just write some messages into it using pw.println. And then I'll just print out some numbers side by side with spaces in between, and then I'll print a new line. So I don't have a haha file in my home directory right now. If I go ahead and I run this, I've got a haha, and there's my output. So it's really no harder than using println to print a standard out. You just create the Printwriter object once and close it at the end. All right, good on that? And I think I put this on the code area that you can get to on Canvas. I think I put that code we just had. All right, let's just take a quick look at this tree map business. So a tree map is basically a hash table. Okay, it's like a hash map. It has pairs of keys and values, and with each key we can associate a value, right? But it's organized internally in some ways like a tree, so we can also do searches. A normal hash, we don't really have a nice search mechanism. You take a key, you hash it into an index in an array, say, and you store your data, your value at that index. You take another key, you hash it into an index, you store your matching piece of data at that index. And so a normal hash is very efficient for searching. If you want to find a key, we can just hash its key, look in the array, see if the value is stored there. So search is okay, but if we want to do something like pull out data in sorted order, there's really no natural way to do that in a hash. Because the stuff that's stored in your array is inherently not sorted, right? It's sorted by the hashed value, and hashing is taking a key and turning it into some bizarre version of itself. So a tree map lets us deal with a hash but pretend that it's sorted in some way. And so we can tap into methods such as first entry and higher key. So we can get the first key according to an ordering, and then we can pull out keys in successive order. So just for kicks, and since some of you already did this, I thought I would code up the previous programming assignment, okay, the word list, using a tree map, and this is basically it. So it's 28 lines, including comments. But this is a cool example because it's really using objects as sort of fundamental entities. Right, we are comfortable making an array of integers. We're not always necessarily as comfortable making an array of structures, right? Or making an array whose entries are arrays of structures. Or making a linked list whose nodes contain arrays whose entries are arrays of structures, right? And if you can be in that mindset where you sort of see this object as just an object, no different from an integer or a character or a string, and you can sort of carry it around in your mind and just plop it into a linked list or a tree or a hash, right? You're unlocking a lot of potential power in writing code. So so all the stuff in the top, this is just imports and declaration of the class and the main and the scanner setup. And here's the first spot where we actually get into something interesting. Which is here at line 10. So here we're constructing a tree map. Okay, so tree maps come with two things, keys and data. Right, and with each key we associate a piece of data. Well, the key here is going to be a string. Okay, that's what this first thing in the generic specifier says. So the keys are strings. The data is an array list. Okay, so this is a hash where we have a key mapping to a value. This is a string. This is a linked list. And linked lists are generic, so we have to say what kind of linked list. And in this case, I said it's a linked list of integers. And this is what we were calling a position list. And this string is a word from our input file. So this structure is taking each word in our input file and letting us get to a linked list of locations, positions associated with that word. That's exactly what your word list structure was, right? It is a way to take each word and find a list of locations.
Now it's all in one line.
And now it's all in one line. We're saying I'm going to make a tree map. It's going to be called word list, and it's going to be comprised of keys, which are strings, and values, which are linked lists of integers. So we still have to keep track of the position of each word as we read from the file. So while there's another token available, we read that next token and I store it in Word. And remember, there are two things you had to do. If that word was already in your list, you just wanted to add a new reference to it, add something to the end of the position list. If it wasn't in your list, you had to add it to your list in the correct spot, create a new position list, initialize one node in that position list with whatever the current position is. And that's what this does right here. So word list is an array list. Sorry, it's a tree map. And tree maps come with a contains key method. And we can give it an object of whatever type the key is, in this case a string, and it will tell us if there's anything in that hash that matches that key value. And if there's not, so I'm negating the condition here, if the word list does not contain that key, then I go ahead and I put it. So what do I put? Well, put takes two things. It takes a key and a piece of data you want to put associated with that key. So the key is the word, and the piece of data I put is a new array list of integers, an empty linked list. So once I get down to this spot in my code, I know that my word is in my word list. I either found it or I just put it in that previous statement. And I know that there's a position list associated with it. And if I just put the word in, that position list is empty. If the word was already in there, it's a valid position list. So now to add my new position takes a single line, which is right here. So I go into my word list, I say get the piece of data associated with my word. That's a linked list, or an array list. I grab its add method, which says add something to the end of the list, and what do I add? My current position plus 1. So I pre-increment, store that in my linked list. So here's the whole workhorse of the code that reads each token, updates the word list. And when you come out of this loop, you've hit the end of your input. Your word list has been built. So we go ahead and close the scanner. And PA2, you didn't actually, or PA3, you didn't actually print this out, right? But you had a method for it. But I just printed it here just so we could look at it. So how do we print the results? So I use the first key method to find the first, according to the alphabetical sorting of the keys, to find the first key, and I set that equal to key. And if it's null, there's no data stored in my hash, so I don't do anything. Otherwise, I print out the key, I print out a colon, and then I concatenate to that what happens when I call the get method on that key. So word list is a tree map. Tree maps have a get method. They take a key, they return a piece of data. So this wordlist.get parentheses key returns a piece of data from my tree map. Well, what's the data part of my tree map? It's an array list. So I'm concatenating the list of positions to this string. And array lists come with a toString method that if you try to turn them into a string, it gives you a nice list of the data value of each node using the toString method for whatever type of node you have. And so this will give me my nice list of positions. And then I say, okay, change my key to be whatever the next higher key is. So the next key in the sequence, and go back up to the top of the loop. So these lines right here basically iterate through my word list, print out each word followed by the list of positions. And that's your whole program.
So when you say key, it's returning the word, and when you say get key, it returns the array of numbers?
Correct. Or whatever data you've associated with that key.
Okay. This is all happening in two-string. That's interesting.
Yeah.
Because I
So
feel like if you casted something that wasn't a string, would key still, what would key be then?
key will be, so if you look at first key, it returns an object of type K.
Okay.
Okay, and K is when you set this thing up. It's the type of keys. So when you construct, and when you declare, you specify these two things because it's generic.
Yeah, I get that. 'Cause that's just the, that's just happens to be the value that it sorts by.
Yeah, yeah.
Sure.
So if we run this, if we try to run it,
Could you put more than two data structures in engineering? If
you
were-
can define generics with as many as you like,
Okay.
right? So some generics only take one parameter, some take two, some will take more.
I could make an array that had integers and strings. It would just, would that work?
Are you talking about creating your own generic class?
Well, I'm saying if I wanted to make an array that had a data that had two things in it, kind
Mm-hmm.
of.
Like a two-dimensional array thing? Or not really?
Sort of, like, just like how you're tying the numbers to the words. If I
Mhm.
have a list of the numbers and words, could I just make it an array with int common string?
Sure.
Cool.
But you'd need to make your own class for that,
Oh, okay.
right? Because arrays aren't inherently generic, right? But you could make your own type of array that is generic, and but I mean you can also just make
I didn't mean arrays. I meant
lists.
just list. Yeah.
Yeah.
Did you? Okay.
Yeah. So when you construct a linked list, you give it one parameter, right, which says what type of objects are we storing in the data piece of each node, and that can be a primitive. It can be an integer or some other object class like that, or it could be a class you define.
Okay.
So you could say, okay, my nodes are going to contain a string, a double, and a TreeMap, right? You can make a class that has those fields, and then say, here's a linked list of this type of object. So I just fed it its own source code here, just for kicks. And so if we run that, we get an index of its source code. So look at all them comments. Look at that. This is how I should grade your code. I should just put it in here, and
At least 10
and you get a point for each comment. How about that?
Oh, cool. Extra credit.
Yeah,
That'd be an automatic.
yeah, with no limit. I wonder what the longest program is I get.
Well, could easily cheese that by having just one line of your code be slash space slash space.
Yeah,
slash,
yeah,
slash.
that's true.
So, easy to cheese.
Yeah. I still wonder how far someone would go.
You could probably
How many
make a
points is
really,
enough?
Like, in-depth grading program using stuff like that if you never told anyone.
Yeah, yeah, until someone finds out, right?
Exactly.
But I mean, this is what we did in school too, right? We figured out the professors. I spend more time learning my professors than learning the subjects. And so, because we're just programs ourselves, right?
In the end.
All right, so that's something that you want to keep in mind, because we're going to see this again and again, right? This idea of taking a data structure and incorporating it inside a different data structure. And when we're doing that, right, when we're thinking about this in terms of, let's go ahead and print out our data structure here, we're thinking about it as a tree map. We're not really worrying too much about what the data is, right? We're concentrating on the tree map part of it, But down here, when we're trying to augment the data piece, right, then we're thinking, okay, and the data is actually an array list, but we don't really care what the key is at this point, right? So, so this is going to be a recurring theme, sort of being able to compartmentalize different pieces of your data structure. And if you're developing this piece of it, you just sort of take this as, you know, here's a array of linked lists, right? And it doesn't bother me. It's just something I'm carrying along over here. So we'll play with regular expressions in a few days, probably the end of this week, and we'll see another example of this. We'll build some simple code using regular expressions and hash maps and have fun with that. All right, we are out of time, so I will see you next time.